The fundamental counting principle. Our objective? We want to solve counting problems using the fundamental counting principle to determine the total number of possible outcomes in a given situation. Let's demonstrate the fundamental counting principle using an example. Keep it pretty simple so we don't have to write too much. You wake up and need to select something, pants and a shirt, to wear. You have two pairs of pants to choose from. One pair is black, one pair is khaki. And you have three shirts to choose from. We'll go with white, red, and yellow. What is the total number of possible outcomes of one pair of pants and one shirt? Okay. Most people, when they start talking about possibilities, use what are called tree diagrams. So let's do that. You're going to start out and you're going to put on a pair of pants. So we'll put pants here. And your choices for pants, and leave a little bit of space as I'm doing. You can choose the black pair of pants, or you can choose the khaki pair of pants. Okay, once you've chosen the pair of pants, you then go into your closet and pull out a shirt. We'll put shirts as the second choice, going from left to right. If your shirt choices are white, white, red, and yellow. And of course, they go with the black pants. So you can choose black pants with a white shirt, black pants with a red shirt, and black pants with a yellow shirt. And they also go with the khaki pants. So white, red, and yellow. And you can choose khaki white, khaki red, or khaki yellow. So as you see here, there are 6 possibilities, 6 total possible outcomes. Black, white, black, red, black, yellow, khaki white, khaki red, khaki yellow. In this, and you can see this from our tree diagram, there are 6 possible outcomes. If we were talking about a sample space, we just did that, the black, white, black, red, black, yellow, etc. Let's notice something here. Our choices in pants are 2. Our choices in shirts are 3. If we multiply 2 times 3, we get 6, which is the total number of possible outcomes we got from our tree diagram. And that's the fundamental counting principle, which I have down here for you. Get my paper up there. Okay. The fundamental counting principle. If a task consists of a sequence of choices in which there are P selections for the first choice, 2 in this case, Q selections for the second choice, 3 in this case, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R times continue as necessary, different ways. So from the example above, and I'm a big fan of using lines and labels, we're choosing from pants and we're choosing from shirts. And again, I'm a big fan of putting a line here and the item down here. I have 2 pairs of pants. I have 3 shirts. The fundamental counting principle says I'll multiply those 2 to get 6, just like we saw up here. Okay, so let's do a couple of things. Let's do some examples. And we'll see this in action. Probably something you've seen before. The fundamental counting principle tends to pop up with basic probabilities. Probably your first glimpse of this might be in middle school. A pizza can be ordered with 2 choices of size. You can get a medium or a large pizza. You got 3 choices of crust, thin, regular, or thick. And you have 5 choices of topping: beef, sausage, pepperoni, peppers, and mushrooms. How many different 1-topping pizzas can be ordered? Okay, so we have 3 items we're going to select from. Again, I like to put an underline and then to label what those are. So we have size, we have crust, and we have toppings. Okay, how many possibilities are there for size? There are 2, medium or large. How many possibilities are there for the crust? We have 3, thin, regular, and thick. And how many different toppings can we put on this? Well, we have 5 different toppings. And we're doing a 1-topping pizza to keep this simple. So how many different 1-topping pizzas can we order? We'll just multiply those, and 2 times 3 is 6 times 5, and we come up with 30 different 1-topping pizzas. Okay, this example 2 kind of gets us to counting with repetition, which we're going to be dealing with in some future lessons. So the International Air Transport Association assigns 3-letter codes to represent airport locations. For example, the code for Fort Lauderdale, Florida is FLL. Okay, notice you can repeat a letter here, repetition. I could have more than 1 L in this case, or more than 1 letter. How many different airport codes are possible? Well, they are 3-letter codes. So again, I like to use underlines, and this would be the first letter. This would be the second letter, and this would be the 3rd letter. Okay, well, how many letters are there? In the English alphabet, we have 26. So there are 26 possibilities for the first letter. We're counting with repetition, so we have 26 possibilities for the second letter, because it can be repeated, and we have 26 possibilities for the 3rd letter. So how many possible codes are there? Let's multiply those all up. And I did that in advance with a calculator. And the answer is there are 17,576 possible airport codes, different airport codes we come up with. I don't think we have 17,500 airports on the planet. If I'm not mistaken, yeah, I think that's a lot of airports. But I don't know how many we have. I'd be kind of curious to maybe do a Google on that one. How many airports do we actually have? Okay, let's take a look at counting without repetition. 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected will become the chair, the second person the vice chair, and the third is the secretary. How many different committee structures are possible? Okay, well, we're selecting for the chair. We're selecting for the vice chair, and we're selecting for the, how do you spell secretary? With an E and then an A. There we go. I'm selecting for the secretary. Now, obviously, once you're selected, you're not going to get selected again. You're not going to be the chair and the vice chair. Once you're selected, you're out. So we have no repetition. How many possibilities are there for the chair? Well, there are 14 people. They're all in the hopper to be chosen. There are 14 possibilities for the chairperson. The second person is the vice chair. Well, you took one of them out. One of them is the chair. You have 13 left to choose from. So there are 13 possibilities for the vice chair. And similarly, now you've taken out one person to be chair. Now you've taken out one person to be vice chair. That means you have 12 people left to choose from to be secretary. So many different committee structures. Let's just multiply those. And again, I already used a calculator. There are 2,184 possibilities, different structures possible. Okay, let's introduce a term. Let's introduce a math term that we've kind of been using called the factorial symbol. Again, chances are good you've seen it. Perhaps maybe this one in early high school math courses. If n, which is greater than or equal to 0, is an integer, the factorial symbol n factorial is defined as follows. N factorial is n times n minus 1 times n minus 2 times, and then 3, 2, 1. So basically you start with n, and then you multiply every number down to 1 after it. A couple of points to remember: 0 factorial is equal to 1, and 1 factorial is equal to 1. So let's take a look at how factorial comes into play using the fundamental counting principle. You have just been hired to represent Greenville Tech. On your first day, you must travel to 7 area high schools to introduce yourself. How many different routes are possible? Well, you're going to 7 high schools. So we got 7 lines. 1, 2, 3, 4, 5, 6, 7. Okay. Your first high school, there are 7 choices. Okay, so this is your first school. All right, there are 7 choices of that first school you go to. Once you've been to the first school, your second school, there are 6 choices of how to get there. Okay? Once you've been to the second school, the third school you're going to, there are 5 different schools you could choose from and how to get there. And you probably see the pattern. The fourth school, there are 4. And it turns out that, oops, I meant to say 5th. I meant to write 5th and I wrote 3rd. The 5th school, you're now down to 3 different ways you can get to it. The 6th school, you're now down to 2. And then, of course, going from 6th to 7th, there's only 1 possibility. There's your 1. And so the fundamental counting principle would say this times this times this times this times this times this equals, and the answer is 5,040. Okay, well, 7 times 6 times 5, starting at 7 and multiplying by every number below it down to 1, which is what this says, is the exact same thing as 7 factorial. Okay, so 7 factorial, and this often is on your calculator, the factorial symbol. 7 factorial is quicker probably than doing 7 times 6 times 5. 7 factorial, of course, is the exact same thing, 5,040. So there are 5,040 different routes, different ways you can go to those 7 schools and introduce yourself. So there you have it, the fundamental counting principle and the factorial symbol, both of which are going to be used in upcoming lectures.